So now let's look at X-ray lithography. So X-ray lithography was introduced in the 1970s, by a group from MIT. So this person, so his name is Henry Smith. So he is still very active even today, and I saw him in the conferences, and he is actually my supervisor. So I think he is probably the top figure in the field of nanofabrication. So as you can see, back in the 1972, this is 1 year after my birth. So people get 50 nanometer lines using X-ray lithography. This is extremely high resolution in the 1970s, so 50 nanometer lines. So for the figure on the right, so this one shows that we have very high depth of focus. So the top and the bottom, they are both well defined. That means actually they have very well depth of focus as well. So I'm sure everybody knows very well about X-ray. So X-ray was discovered in 1895. So one question I want to ask is the difference between X-ray and the gamma ray. So I'm sure you heard of gamma ray as well. From this figure, it looks like the difference is the wavelength higher than one angstrom is called X-ray. So the wavelength lower than 1 angstrom it is called a gamma ray. But actually nowadays, so the definition a little bit different. So X-ray is defined as the electronic process. For example, so when an electron gets accelerated or decelerated, or electron transition from one energy level to another energy level to emit a light, so this is called X-ray. So gamma ray means a nuclear process. So for example, when there is nuclear reaction, when the lights come out because of nuclear reaction, it is called a gamma ray. And also we know that inside the nuclear, there is also energy levels just like outside of the nuclear. So the proton and the neutron inside the nuclear, they also have this orbital movement, a kind of orbital movement. So when they transit, proton or neutron transit from one energy level to another energy level, it will also emit the light. So that's also gamma ray. So this, in short, nuclear process gamma ray, electron process X-ray. So this is the basic setup of X-ray lithography. So as you can see, it's very simple. So here we have the wafer coated with the resist. So here we have the mask. This is similar to the photo mask. The setup is similar to the photolithography. But the difference is that, one, for the normal proximity optical lithography, so we have a broad beam. So the beam is very broad. But for the X-ray, the beam from the synchrotron radiation, the beam is not broad. So we have the beam size is not so big. So we have to we need to scan the beam across the mask surface. Secondly, for the normal optical lithography, so the photomask is made of absorber and substrate. Here there is also absorber, it's the same thing, but here this one is the membrane rather than a thick glass. We know for the optical lithography, this part is the millimeter thick coarse glass, but here is the very thin membrane. But anyway, so this is a kind of optical lithography because we have X-ray light shine through the mask onto the resist. So the resolution is the same formula here. Roughly lambda over G, lambda G square root of lambda G. G is the gap. But the difference is that very often the gap here is much smaller than the resist thickness. So we can use millimeter thick of the resist, but the gap may be a few micrometers. So in this case, the G is small, thickness of the resist becomes very large. So here is the key point of X-ray lithography. So we use smaller wavelengths. When we have smaller wavelengths, there will be less diffraction. Then we get better resolution. So we have better resolution, as you see here. Secondly, because the X-ray there is no backscattering of reflections. We know for the light can be reflected back. And for the electron or the ion beam, so we will learn about electron or ion beam lithography in chapter 5 and 6. So the charged particles, they can be scattered, but for the X-ray, it will not be scattered. And it has very large depth of focus. That means the resist top and the bottom, they can both remain well focused. And it is simpler. It is very simple. So all we need is the acrylic source and the acrylic mask. As you can see here, we just need the source and the mask. We do not need any lattices, stated, complicated things. It's very simple. For the limit, so first it is 1 times mask. That means you can see here the feeder size. So the feeder size on the resist is the same as the feeder size on the mask. So it may be hard if the feeder size here is very small. It may be difficult to fabricate the mask. But we know that for the normal DUV lithography, so we have 4 times reduction by the length. So this makes the mask fabrication easier. Secondly, the mask is difficult to fabricate, and there are lots of problems because this one is only for the high resolution acrylic lithography. This one is only about 100 nanometer thick. So you can imagine 100 nanometer thick over many centimeter size. Then it will be very fragile, and it can be distorted, bended because of heating and other problems. A third major problem is the light source. So for the acrylic, we need a strong, stable, collimated source. So the only good source is the synchrotron radiation. The synchrotron radiation can have those very strong, stable, and collimated acrylic source. But we know that for the synchrotron radiation is very costly to build. It will cost, I think, several $100 million to build a synchrotron radiation setup, and it's also very big. Take like the football field, like the size of a football field. And resolution is still limited by the fractional diffraction. So here you can see that we still have this formula here. So lambda can be very small, but the gap cannot be too small because when this area is very big, it's difficult to maintain a small gap, and we cannot have close contact. If the mask gets contact if the wafer gets contact to the membrane mask, the mask may be broken. So as a result, the gap may be tens of micrometers. So we have tens of micrometer gap here, even though the lambda is very small, so the resolution may not be that small. Lastly, the resist is not sensitive. Normally, we need a very long time to exposure. For example, we may need a few hours to expose one wafer. But we know that for the DUV lithography, the throughput is 100 or even 200 wafers per hour. But here, it's like 1 wafer per hour, very, very slow. As a result, this one, acrylic lithography is not used for the IC high volume manufacturing. And now we look at acrylic source. So this one, the first source is the electron impact source. So this one, I'm sure you are familiar with it. So we have electron hit a target. So the electron will kick out. This one is E1. The E2 is the one kicked out. So when this electron kicked out, so electron from outer shell, here from L shell, will jump to this lower shell. Then at this process, a light may be emitted. So the light will correspond to the X-ray. Another possibility is that energy from here to here is given to another electron here. So this electron in the M shell will be kicked out. This energy here is given to this one kicked out. So this is the OJ electron. So for the case of acrylic emission, so here is the typical spectrum. So for the electron energy level, so we have K, L, M, N, those electron energy levels. So everything jumps to the K level is called the K. So L to K is called the K alpha. M level to the K level is called the K beta, and then you have K gamma, etc. Jump to L, we have the L alpha, L beta is the same. So for the case of K alpha line, the K alpha line is from the L level to the K level is given by EK minus EL, 13.6. So this is not 13.56, it's 13.6 Z squared, the energy level difference. So we have seen that. So normally the energy level given by Z squared over N squared. So then Z squared over N squared. Then we have this number 13.6 in the front. But here we have the Z minus 1. So this is because of the screening effect. So there are 2 electrons. So we know for the K shell there are 2 electrons. So when one is kicked out, there is another one. So when this electron jumps to this K level, it will see the other electron. So the remaining electron will effectively screen or shield the charge on the nuclear. So that's why we have this Z minus 1. But normally, this one is replaced by Z minus sigma. Sigma is the screening effect of that remaining electron. So then this one given to this 10.17 Z11 square. So this is the K alpha line for the rough estimation. So this number here should be, as I said, 13.6 is not 13.56. So I get messed up for this number because we know for the normal RF source, when we do the spectral separation or when we do etching, reactive ion etching, so we have the RF source. So the RF source has a frequency of 13.56 megahertz. But here the number is not, should be 13.6, not 13.56. So this one electron impact accuracy source was developed in 1912 by GE. So this is the setup. So we have the hot filament. The hot filament will emit electrons. Then we have high voltage. So electron will be accelerated to bombard the target. Then actually will be emitted. So the issue is that first the power is low. So this kind of accuracy tube, the power is low, but it has very narrow emission. So it's single wavelength. For example, we have K alpha is very narrow peak. So this one can be used for the accuracy diffraction measurement, and also can be used for the medical imaging. So how to increase the power? So one way to do this is to have this kind of setup. In this case, so we have the refractory anode. This metal can tolerate very high temperature. Secondly, it's fast rotating, so the heat can be dissipated. And also we have the water, cooling. So this way, because we have very good heat dissipation power, so we can have very high current bombard onto the target. This way we get higher emission of the X-ray. So this is X-ray tube, used for the research, but not for the X-ray lithography. So for the X-ray lithography, we need much stronger X-ray source. So this is the case for the synchrotron radiation. So this one comes from the electron they move in a circular movement at very high speed, very close to the speed of light, relativistic speed, very close to the speed of light. This one is also observed by the GE. So this is a GE General Electric. This one is the same. It's also from GE. At that time, in the 1940s, so people used the synchrotron radiation to study particle physics. So they want to give electron as high energy as possible to study some fundamental physics, particle physics. But because of this radiation, so it is difficult to accelerate electron. So when we give energy to the electrons, it does not get accelerated that much because it lost energy as the radiation. So at the beginning, it is considered as a waste product, limiting the performance of the accelerator. But later on, people see that this radiation is actually the best light source. So this one has a very good infrared, visible UV light, deep UV light, back to X-ray source. And this is the best light source that we can have. So as a result, so today, a synchrotron radiation for the case of electron is not used for the fundamental studies of the particle physics. It is more used for the light source. So the one in Canada is called Canadian light source. So the Canadian light source synchrotron radiation is built in the Saskatchewan. So the radiation is highly polarized and pulsed. So when the electron move, so it will stay here. So only when the electron move here, you can see it. So when the electron moves away, you cannot see it. So as a result, you see it is pulsed, not a continuous wave. So here give you the explanation of how synchrotron radiation works. So here is the same thing, but in a simple, you can see the clearer here. First, we have a bunches of electrons. We do not give the continuous electron current in the string. So we have a bunches. So each bunch is picosecond pulse, picosecond bunches spaced by the nanosecond apart. So this bunches of electron is generated by the accelerator. So this one can be linear accelerator, low energy linear accelerator. So linear means electron move along a line. This synchrotron means electron move in a circle. There are many bunches of electrons moving inside this circle. So how come electron get accelerated? This is done by the this one. So this electrical field will speed up the electron. But here you can see it is RF. RF means a radio frequency. Radio frequency is in a megahertz radio frequency. So in principle, you may think that we can have something like this. We can have parallel plate. So we have a hole, electron come in, right? Electron come in. If we have a hole, if we have aperture here and we have aperture here, the electron can pass through. If this one we got positive charge, this one we got negative charge. When electron come inside, it will be, this one should be negative charge. This one is positive charge, because electron is negatively charged. But this negative charge, positive charge. So when electron come in, it will be accelerated. This way you can have energy. But here you can see it is wrong, because here those parallel plates do not lose any energy. It's just a charge. But electron gain energy. So electron cannot gain energy from nothing. So energy is not conserved. So we cannot have this kind of setup. So what we need, we still a parallel plate, but we apply an external voltage here. Now this voltage is RF, not DC voltage, it's RF voltage. That means so when the electron come inside, the electrical field point up. We know electron is negatively charged. So when the electrical field point up, electron gets accelerated. When the electron go away, so when the electron moves to here, the field get point down. But when the electron come back again, the field get point up again. So this way, electron always get accelerated inside this parallel plate. So it gain energy. Then you can imagine the switching field, the frequency of this RF equal to 2 pi r divided by the speed. So this is the period. So the period of this RF frequency is given by 2 pi r divided by the speed. The speed here is very close to the speed of the light. So now we come back. When we have this DC, if the energy is DC, so we can see inside it may be accelerated if there is a charge. But the problem when the electron is outside, is here, it will be decelerated when we have the case for the DC. But for the case of AC, we don't have this problem. So the critical energy, so the critical wavelength for the synchronous radiation is given by this formula. So we will see this formula again. So each of them you can see is pulse, a very narrow picosecond pulse. They are nanosecond apart. So this is how the synchrotron is radiated. But there will be no radiation between the magnet. So here we have one called a bending magnet. So when the electron is bended, it will emit the light. Then it goes to the straight line. And when the electron goes along the straight line, there will be no radiation. So this one is also magnetic. This is also magnet, but this is the wiggler and undulator. So we will see the wiggler and undulator later on. So how come we have the radiation? So radiation is caused by the charge acceleration. So some people may think that when the electron moves really fast, it will move near the speed of light, and then it may emit. For instance, we have if the electron move at 0.9 c, very fast, it may emit the light. But actually, even though you have 0.9 speed of light, there will be no emission, because we know the speed is relative. So the speed here you see 0.9 c, but if the observer move at 0.9 c, then he will see the electron as static, no movement. Then there will be no emission. So the speed is relative. So what is the absolute is the acceleration. So the acceleration of the moving object, this one, the number here is absolute. So when there is acceleration, there will be radiation. When there is speed, very high speed, there may not be a radiation. So for the case of the synchronous radiation, the electron move in a circular fashion. So the acceleration is given by a v squared over r. Then there will be emission. For the antenna, a radio antenna. So we have the antenna here. So electron move up and down movement. So when the electron move up and down, there is also acceleration. then there will be emission of the electromagnetic wave. So here is the same idea. So only when charged particle get accelerated, there will be radiation. Otherwise, there will be no radiation. So obviously, the radiation will depend on the acceleration. As you can see, that this is the radiation power per solid angle. This is the spherical angle. It's also called a solid angle. So it's proportional to the a square. So we need the acceleration for the radiation. So here we have sin theta square. So here is the theta angle. But this is this is the radiation direction. So as you can see, for the perpendicular direction, we have the maximum radiation. Along the acceleration, theta equal to 0 degree, there is no radiation. So this is when the movement in the orbital movement. So A is point to the center of this orbit. Then the radiation will be something like this. The same formula here. So this is the case for the case of the speed is much smaller than the speed of light. So when the speed of the charged particle is close to the speed of light, so we have a relativistic case. In this case, the radiation will be folded forward. And this is like a laser, like a laser. So very collimated directional radiation, like a laser beam. So the cone angle here is given by 1 over gamma. So we will see gamma later on. Well, gamma is a very big number, a few thousand. You can see. So it is a very collimated directional radiation. So here you see that. So when we have the acceleration, there will be radiation. So now we come back. So we come back here. So what will be the spectrum coming out from this X-ray tube? What will be the spectrum looks like from this X-ray tube? So people may think it should be something like this. So this is the energy. This is the loss. So we have maybe one peak here, another peak here, something like this. This may be K alpha, F alpha, M beta, this kind of spectrum. So we have the peak. So those peaks come from those transitions. So actually, we have not only those peaks, that is called a characteristic X-ray. There is also a big background, something like this. Background. So that means we have the peak emission, we have the peak, we also have this big background. This big background comes from the deceleration. So when the electron gets hit the target, it will be stopped. So when it's stopped, so we have a very big value. So the value will be negative sign, very small, very big negative acceleration. That means electron has a very big deceleration. But here is the square. So even though A is negative value, we still have very high radiation. So there will be a lot of radiation because this deceleration number is very high. So you can see electron hits the target, gets stopped right away. So we have a very big A number. So now let's look at the spectrum from the electron tube. So those are the spectrum of X-ray tube. If you take any of them, you take this one. So this for the gold, is for silver. You have this background. So this background is caused by the deceleration of the electron when it hits the silver target. So we have this background, and also we have this characteristic X-ray. So this for the silver. So this one is for this one is not, I'm not sure which metal. So this one is tungsten. So this one from tungsten. So we know that the X-ray is used for the radiation therapy. For the cancer, people use radiation therapy to cure the cancer, to kill the cancer cell. So actually, the radiation therapy to kill the cancer cell comes from this background. This background is more efficient, more energy for the radiation therapy. In Waterloo, there is the radiation therapy in the Grand River Hospital. So they have the X-ray tube in the Grand River Hospital to cure the cancer. So now let's look at X-ray the synchronous radiation spectrum. So here the y-axis is the photon. Photon is the per second per solid angle per current of the electron. So when the electron moves in the circular in the storage ring it has the current. Then per 10% of the bandwidth. So bandwidth means delta lambda over lambda, something like this. This is the photon energy. So this is my photon energy. So here 1 kilo electron volt gives 1.24 nanometer wavelength. So this one will be 1.24 angstrom, 1 angstrom wavelength. So this is the photon energy. So the number here is electron energy. So electron move in the circular in the storage ring. This is the energy for the electron. So you can see the energy for the electron is very high, giga electron volt. For the giga electron volt energy in the electron of the electron give you kilo electron volt photon energy. So the critical part, so the turning part is given by this formula. The critical energy given by 2218 E. This energy is the electron energy. Divided by R is the radius of the storage ring. So we know that for the E is given by hc over lambda. This is the Planck constant, speed of light divided by lambda. This is the energy for the light. So here we use the E as the energy taken as the electron volt. So when we turn to electron volt, we have another number here, electron volt. If we have this number here, you get 12398.5 1 over lambda. So H, we know the number H and the C and the E. So we have this formula. Here lambda C is angstrom. So here lambda C is nanometer. In nanometer different, a little bit different. Given by this formula. So this is the signal to radiation spectrum. So higher electron energy, you can get to higher X-ray energy. For the one in the Canadian light source, so I believe it is a 3 giga electron volt. So now let's look at how fast electron move in the circular for the signal to radiation. So we have said that electron move at the speed very close to the speed of light. Now we want to know how close it is the movement to the speed of light. So we know the electron rest energy is given by mc square. mc square given by 0.511 mega electron volt. So this number looks very big, but actually compared to the giga electron volt, so this number is very small. So when the electron move at the relativistic speed, the total energy is given by gamma mc square. Gamma is given by this number, gamma mc square. So this number here, 1.5, is given by gamma mc square. mc square equal to this number. So gamma is given by this number. For example, so when we have 1 giga electron volt, this is not too high, here not too high. Gamma is given by 1000 divided by 0.511, 0.511. Giga means 1000 of the mega. We're given this number. Then from the gamma number, this number here, you can find out the V over C equal to this number. So as you can see, the speed of electron is usually close to the speed of light, as we have mentioned before. Now let's see whether this formula makes sense or not. Gamma mc square. So what will be the case for if the V over C is small? If this one is much smaller than 1. If this one is much smaller than 1, the total energy should be 2 terms. The rest energy plus 1 over 2. Right? So when the speed of the speed much smaller than the speed of light, this we go to the normal situation, not relativistic situation. Then the total energy should be given by mc square plus 1 over 2 mv square, the kinetic energy, rest energy. So now we want to see whether this is actually the case or not. So now we need to do the approximation for this term. We have 1 minus x 1 over 2. 1 over 2 power 1 over 2. Okay, this one. So this one is approximately 1 plus 1 over 2 v square over c square. So v square over, so this one v square over c square, v square over c square is the x here, roughly equal to this one. But generally, so we have 1 plus x y equal to roughly 1 plus x, y. This is the general case. Now here we have minus sign. Here x equals to minus x, y equals to 1 minus 1 over 2. So we have this number here. Generally, we have the approximation like this. You can see whether this makes sense or not. When y equals to 1, so we have 1 plus x, so it makes sense. If the y equals to 2, if y equals to 2, 1 plus x squared, then equal to 1 plus 2x plus x squared, right? So for the small x, so when the x is small, so this term can be ignored. So we have 1 plus 2x, so 2x, so you see 2x, so 1 plus 2x. If we have 1 minus x, this one for instance, 1 plus x, then this one equal to roughly 1 minus x, right? Roughly equal to 1 minus x. So when we ignore the x squared term, we have 1 minus x. And this also is like to 1 x. Here the y is like a minus 1, so we have 1 minus x. So generally, so we have, as we said, 1 plus x y equal to 1 plus xy, roughly. When x and y, when x is very, very small, this will be the case. That's why from here we know we can go to the classical case that we have the energy, total energy given by mc squared plus 1 over 2 mv squared. So far we have seen it's called a bending magnet. So we have one big magnet. We have this bending magnet. So electron pass through, and it will be bended. There will be emission of the X-ray. So this one energy is still not high enough. If we have the regular or undulator, the emitted light will be even much stronger. The regular or undulator, we have many pairs. Of the magnet. So when the electron move below the magnet, it will bend it here, bend here. There are lots of bending. At each of the bending, there will be emission of the light. So when the bending, there are so many of them, then the total radiation will be smaller, much stronger than using a single magnet. So I remember the difference between regular and undulator is that when those radiation they interfere constructively, it is undulator. You get much higher radiation when you have the undulator than a normal bending magnet. You can see. So here the brightness. The term is called the brightness. The brightness is the number of the photons in given bandwidth per second per milliradians, say the milliradians phi. This is the solid angle, spherical angle or solid angle per area of the emission source. If we have this is the area of the size of the source. For the case of the sun, this will be very big area. But for other, it will be small area. But this is the source. This is the area on the source, not the area on the detector. So the brightness for the sun is 10 to the power 10. So for the advanced red source in Berkeley, this one give you a 10 to the power 19. It's 1 billion. So 1 billion times stronger than the sun. So you can see here the same thing. Very high radiation from the signal radiation. So much, 9 orders higher than the radiation from the sun. And this is a spectrum. Okay, thank you. So now let's so we have mentioned that signal radiation is more used for the red source than for the fundamental study of the particle physics. But this in Canada, so we have this Canadian red source. This one is in Saskatchewan. So I visited this place December 2019, last year December. Let me see. So here the beam lines. So here the drawing of the beam line. So this is the electron move in the circular way. The size of this one is maybe 10 or 20 meters, 10 meters. So this beam line is called Silman. So this one is used for the X-ray lithography. So others, they are used for different purpose. So each of the beam come from we have this magnet here. You have one beam here. There is another magnet. So each of the beam line will correspond to one magnet. So now let's look at what we can do with the actually synchronous radiation. So we can do so many different things. For example, we do this diffraction anomalous fine structure. Actually, fluorescence. This is actually fluorescence. We can also do the actually microscopy, actually absorption fine structure. This is absorption to study the material property. We can also do the actually diffraction, RD. This is actually diffraction, macro CT. So do you see how many things? This is also diffraction, fine structure, actually scattering, diffraction, absorption. Yeah, so we can do so many measurements using the synchronous radiation. And this place is free. So you can submit a proposal. You can submit a proposal to this place. So if you need to use to have some fancy results for your research, you can submit a proposal to this place. Then they will do the measurement for you, and it is free. But when you publish the paper, maybe you put the people from the Canadian red source as the co-author. So this one is the Canadian red source. So this one is CERN. So this one is CERN. This is in a place near Switzerland, near Geneva. So I visited this place maybe 5 years ago. But this one is also synchrotron, but it's not electron. Inside here is a proton beam. So proton beam do the circular movement. So this is for the fundamental study of the physics. So the orbital for this proton beam is 27 kilometers. So this 27 kilometers is in the under the city of Geneva. Total perimeter is 27 kilometers. So if you remember, so this place they got the they discovered Higgs. Higgs is the Nobel Prize a few years ago. So again, this is it's also synchrotron, but this is not for electron. It is the for proton, for the fundamental study of the physics. So this is inside the inside this place, inside the orbit. I think this is the orbit. So proton should be moved inside this orbit.